Welcome to our 8 a.m. press conference, our first of the day. This press conference we've entitled New Findings, New Enigmas, NASA's Van Allen probes begin their exploration of the radiation belts. And to introduce the speakers, we have Nikki Fox. She's the Deputy Project Scientist for the Van Allen probes. She's from the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland.
Thank you. Good morning, and thank you for coming to our fabulous press conference. I think you'll be amazed at the quality and the amount of results that we have when you consider that the mission is not even yet 100 days old. We'll have our 100th day birthday this weekend, and we have tremendous results to share with you today. So just go to the first slide, please, Jeff. So I just wanted to kind of give you a quick, in a nutshell, obviously this is more information for you to take away, but about the Van Allen probes. So we are recently renamed. We were the Radiation Belt Storm probes. We launched August 30th of this year, went through a 60-day commissioning, and went operational at the end of October. There are two spacecraft. They are identically instrumented. The reason that we have two is so that we can distinguish things that happen in time and things that happen in space. If you go through a region and then you have to wait 9 hours to go through it again, you really don't understand the dynamics. But having two spacecraft going through allows you to really unlock the mysteries. We have a very low perigee. Our closest point to Earth is 600 kilometers, and then we sweep out. We have a very highly elliptic orbit going out to almost 6 Earth radii at the furthest point. That allows us to sweep through the inner belt and the outer belt to fully look at the dynamics of both of the regions. We go round in 9 hours, so that is well within storm time, so we actually get to go through and sample a number of times during the storm. We're a 2-year mission, and that's so that that point that's the furthest away from Earth, Jeff, if you can just point to the apogee for me, that point that is the furthest away from Earth actually precesses. It moves around so it sweeps out through the entire region going around the Earth. So it's a bit like if you imagine a child's spirograph doing petals of a flower, and you fill in all the petals as you go around. It takes just under 2 years for us to do that, so we are able to sample all of the regions of the radiation belts. We are very low inclination, so we're in the equatorial region as much as possible, and we do have a space weather broadcast, so you can follow our data in real time. Thank you, Jeff. Again, mostly for information, but our overarching goal is to understand how these radiation belt particles, why they exist, how they form, the radiation belts form, and how they change in response to what's coming to us from the sun, with a goal of ideally being able to predict this. It's got a lot of impacts. We are obviously a fundamental science mission. We're doing particle acceleration. It's the same type of processes that take place all over our solar system, even beyond causing the Crab Nebula to glow in X-rays. It has very practical applications, space weather, allowing us to design radiation-hardened spacecraft better by improving models. It actually is finally, this is a mission we've been waiting for 50 years. We know what's there, we think we know what's there, now we can really go and measure it. So we'll be resolving the age-old questions. Next slide, please. So it is my great pleasure to introduce you to our panel this morning, and I know that they're all very anxious to share their great results with you. We have two main classes of instruments on the spacecraft, those that measure particles and those that measure fields and waves, both magnetic and electric. On the diagram there, I've just highlighted the instruments that you'll be seeing data from today. So representing the particle teams in the outer belt is Dr. Dan Baker. He's from LASP at the University of Colorado in Boulder, and he is the principal investigator for the REPT instrument. That's the Relativistic Electron and Proton Telescope. So welcome to Dan. In the center, we have Dr. Craig Kletzing from the University of Iowa, and he is the principal investigator for the emphasis instrument. So that is a suite looking at both fields and waves, both electric and magnetic for the waves. He will also be presenting data from the EFW instrument, which is our electric field instrument. Finally, Joe Mazur is also The PI of, he's the relativistic proton spectrometer. It's the very, very high energy instrument that is targeting the inner belt. So with that, I will thank you for coming and also thank the Sun for giving us such great inputs to be able to show you this great data today. Dan.
Good morning. Welcome to everybody. It's my privilege to start by showing the launch. This launch occurred on the 30th of August of 2012. And it was a beautiful nighttime launch on an Atlas V vehicle. And quite spectacular, as you can see from this video. The idea was to, of course, launch the two spacecraft together so that they would be deployed in nearly identical orbits, as Nikki has talked about. And everything, after a couple of days of weather delays and other kinds of issues, the launch took place perfectly, and it was a perfect placement of the spacecraft. Quite early began to deploy antennas and so forth, and now you see a portrayal of the orbit here, the elliptical orbit that Nikki's talking about. And now you see overlaid on the magnetic fields the radiation belts as we expected to see them. In fact, our expectation was, at this particular time at least, that we would see relatively placid, quiet belts, and I'm going to show you in a second something that contradicts that. So the two spacecraft are trailing one another, moving further apart, and so if we go to the next slide, this is the cover art for a new book that's coming out from the AGU. It's a book about the dynamics of the Earth's radiation belt, and it portrays the inner green inner zone and the purple outer zone. The two radiation belt storm probes, or now the Van Allen probes, are portrayed in the foreground. The Japanese ERG spacecraft portrayed in the background. And again, this is the picture we sort of expected to see of a relatively placid, relatively slowly developing kind of system. What I'm going to show you next in just a second is some of the data from the relativistic electron proton telescope. We turned on about 2 days after the launch. We had expected to turn on about a month, over a month later, but we were so intent on getting new data, especially to overlap with other spacecraft missions that were coming to an end, that we turned on much earlier. And what I'm going to show you is, if you imagine a plane cutting from the pole to pole at Earth, and sort of one of the cutaway sections there, I'm going to show you data projected onto that kind of meridional plane. So Jeff, the next. And so here is a portrayal in color of the energetic electrons. And so what you are basically seeing here is sort of a block of 3 days worth of data at any one time. A new orbit is laid on, an old one is removed. And this is magnetic latitude versus radial distance, essentially. For those who can see it well, the color bar on the right is a logarithmic scale. So this is 3 orders of magnitude of particle variation intensity seen. And on your left, closest to the Earth, obviously, there is the inner zone that Nikki talked about. The region of relatively low intensity, that is the bluish colors, is the what is known as the slot region between the inner and outer belt. And the outer part, I think you can see, we're going to let it play it another time through, but that's the highly dynamic outer belt, the one that we're really concerned about. These are 4 to 5 million electron volt particles. Electrons of that energy can punch through over ½ an inch of solid aluminum. And so now you see the portrayal here. What we're seeing is a much more dynamic, much more rapidly changing kind of an outer radiation belt than we had really expected to see. And we've got the energy resolution, the time resolution, the energy range, and the availability of the two spacecraft to look at this radiation environment in an absolutely unprecedented way. And we're extremely pleased with what we're seeing so far. And I really urge you, if you're able to come to some of the science talks that will occur tomorrow and Thursday, where we're going to discuss in a lot more scientific detail our present understanding, or maybe better, our lack of understanding of many of the things that we're really seeing with this fantastic new mission. So with that, I'll turn it over to Craig Kletzing.
Thanks, Dan, and thank all of you for coming. Today what I'd like to tell you a little bit about are the electric and magnetic field measurements that we're making on the Van Allen probes. And these are kind of front and center. Not yet, don't steal my thunder.
It's a fire alarm.
So what you see here is a diagram, a schematic of the radiation belts and the various different waves you see. And there's quite a zoo of different waves. In fact, there's several more types than this. Today, I'm not going to try to explain all these different things. I need a chalkboard, and you probably didn't want to hear that anyway. So what I'm going to do is focus on a particular wave mode that we've been very focused on here called chorus, sometimes called the dawn chorus. And so if we go to the next slide, I outline sort of this region where we mostly think the chorus occurs, sort of on what we would call the dawn side. That's the side sort of between midnight going around to the sunlit side of the Earth. And we've known about these waves for quite a long time, but we've never had the kind of measurements that we needed to really understand them, and now we do with this mission, and we're seeing some really great stuff. So you might say, why do you care about these chorus waves? The reason is because they can put energy into particles. And so you say, why do I have a surfer here? And the fact that I went to San Diego as a grad student. Actually, the waves give energy to particles much like a surfer does. And it's not too hard to understand. If we go to the next slide, I have sort of a little schematic of what happens here. So imagine you're out surfing. So if we go to the far right side, if you paddle too fast, well, you go faster than the wave, and that's not very exciting, and nothing much happens. If you don't paddle at all, the wave just kind of picks you up and sets you back down. Again, nothing happens that's very interesting. But what a surfer does is they paddle, so they're going a little bit slower than the wave, but pretty close to the wave speed, and then the wave picks them up and gives energy to the surfer, and the surfer goes zooming out in front. And the same thing happens with electromagnetic waves. Those particles that are moving a little bit slower get picked up by the wave, and the energy gets given to them from these waves, and that puts the energy in that makes radiation belt particles. And so this is the process that we think is going on with chorus, but we want to look at it in detail with this new mission. So the next slide shows this phenomena of chorus. And what I'm showing here are two different views of the thing. On top is what we would call a spectrogram. That is, it's the frequency versus time along the bottom axis. And the bright colors tell you where we're seeing the intense chorus waves. And you see they have this characteristic kind of rising feature. So they're going from the bass tones up to the treble tones. Down below is the actual, what we call the waveform file. And those of you that have ever fiddled with an MP3 file and looked at the waveform might note that that looks very similar. And in fact, it turns out the chorus is in the same band of frequencies as human hearing. And for the first time, we have 16-bit, just like CD audio, measurements of these. So what we can do is take these and turn them into audio, which is what you are now hearing. So this is what chorus sounds like. We've played this clip a bit, but now you see how it looks visually. One of the interesting things, though, about having 16-bit resolution, which we have for the first time, is not only do you hear the chirps, the alien birds, as my wife calls them, but you hear that sort of cricket-like thing in the background. And that was something we couldn't resolve before because we couldn't listen to those very soft things on top of the bright ones. So this is really a fantastic new measurement. And more importantly, we have all the different direction components that we need to know how these waves are moving, and we haven't had that before. My next slide shows a different kind of set of data. This is from the electric field and waves, the EFW experiment. And here what you're seeing are very low frequency waves. And we have seen these waves before. That's not particularly new, but what is new is to understand how long they persist. Most of our past spacecraft would come zooming through the radiation belts. It's not a place that we like to have spacecraft hang out generally, unless you want to go measure them. And what you see here is that the waves persist for up to 5 hours. In the past, it was sort of like watching a car zoom by. You'd get a quick glimpse of the car, but you couldn't see any of the details, perhaps, what the color of the upholstery was. But now we're sitting in the radiation belts, and for the first time, we can see that these kinds of waves persist for hours. And this is very important when we're trying to build models and understand how this stuff works, because if you've just seen it very briefly, you don't really know how to characterize it properly. And so for the first time, we have these kinds of measurements that we need to really understand. The next chart shows chorus again, but in a different format. And so here what I'm showing, on the top is what we call one of the geomagnetic indices of DST. It measures the magnitude of the Earth's ring current. And you see when it starts to dip downward, we start to see activity. The bottom plot shows time matched up with the top plot, but on the vertical axis what you're seeing is essentially the radial distance from the Earth, and the color is showing you how loud the chorus is. And so what you can see here now is that when that DST starts to drop, indicating that our ring current is pumping up, then we suddenly see the chorus waves really start up. And we've never had the level of detail here that we can see. With 2 spacecraft, we're getting good time resolution. We can look at what's happening in different sectors, and we can see the chorus pumps up, and then the DST drops, goes back, rises up to its base level. It starts to drop down, and we can really see this in very fine detail. So that's what I'll tell you about today. It's a summary slide here at the end to say that we're really getting fantastic sets of measurements, and I think as Dan said and Nikki has said, you know, we've just started. We haven't been up for 100 days. Prime mission is barely a month now, and we're seeing some really great stuff, so we're all very excited.
You're supposed to hand it off to me.
Oh, go Joe. This is Dr. Joe Mazur.
Otherwise, I'd just sit here with a dumb look on my face. Good morning. My name is Joe Mazur, Principal Investigator of a high-energy proton spectrometer on board Van Allen probes. And sort of my bookend to this press conference is talking about utility of the mission, not only for scientific use, but also for technological advancement. And the way I like to look at it is to paraphrase what Albert Einstein once said, is that we're trying to keep our wisdom a few steps ahead of our technology. And so that's exactly what this mission's about as far as the focus of my career. And so we've heard about the dynamics of the outer radiation belt here, shown schematically in blue from Dan. And we've heard about the wave fields that we think are responsible for a lot of the dynamics that we've seen. But I'm going to talk about this inner green region here, which is called the inner Van Allen belt. And of course, it's the one that actually James Van Allen measured first on Explorer 1. These are high-energy protons, and their origin is enigmatic. Their impacts can be very severe depending on how much time a spacecraft spends in that region. And it's important for practicality. If you think about our missions to interplanetary systems or anywhere within the Earth's magnetosphere or beyond, any vehicle, space vehicle that we send out has to penetrate these regions to get outside of the Earth's gravitational well. And so if you don't spend a lot of time there, that's fine, but we really need to measure and specify what's going on in the inner belt. And if I have the next chart, and you may say, well, you know, we've been flying spacecraft for many decades now. Don't we know what happens? Don't we know the environment of the inner belt protons? And it's actually sort of a personal story for me. It's not the case. The figure on the left here is a contour plot. Now we've taken very beautiful three-dimensional graphics that we can do today and compressed it down into a really two-dimensional black and white image. This was done by Carl McElwain back in 1963 when I was born. And you can see there the intensity contours of what they had measured as far as inner belt protons, and this is altitude going out to the right. And a few years later, people working at Goddard and Aerospace developed what's called the AP8 model of the same inner Van Allen belt population, but you can see that the contours look drastically different. And that was done during our nation's bicentennial in 1976. And unfortunately, those models have not been updated since then. And so you can see right away there's a huge difference between what was measured 10 years before AP8 came out and what was actually published in the model. So there are huge uncertainties as to what exactly is the proton distribution in space and in energy in the inner Van Allen belt. And it's not very well measured because spacecraft typically don't spend a lot of time down there. It's a very harsh environment. Go to the next chart. But the Van Allen probes have been designed to characterize not only the outer radiation belt, but also survive and work very well within the inner zone. And so this is an example of taking one of our measurement sets from the REPT instrument and looking at the radiation belts not from a cross section, but looking down from the top, from the North Pole. And the intensity there, this is many orbits superimposed on one graphic. The white band there is the most intense proton flux distribution that you can see. And indeed, there is an inner radiation belt. We've known that for a while. But what we're actually able to do now is characterize its spatial and energy extents. If we go to the next chart. And so this is, again, a scientist's way of looking at beautiful nature. He puts it in a two-dimensional plot. We do have movies, as Dan has shown, but this is where we get into the quantitative aspects of how we do our science. And so the leftmost figure there is an intensity versus L shell, and that's essentially altitude. And the black dots show what our measurements are of the inner proton radiation belt. This is greater than 61 MeV protons if you're interested in the actual energy. And so the extremes there, the inner belt starts about 700 kilometers that we're seeing there. The peak intensity is about 6,000 kilometers, and then the figure sort of dies off at about 10,000 kilometers. And so the three vertical bands, the red, black, and the blue, are where we just take samples of what the energy distribution is, and that's what's shown on the right here. So we're looking at the number of particles per unit energy, time, and area versus their energy. And just these measurements themselves are new discoveries because it has not been done across this wide energy range at high altitude ever before. And we're seeing protons up to 1 billion electron volts, and these are the highest energy trapped particles in the Earth's magnetosphere. They're very stable, they're there all the time. I can tell you offline as to what we think the theoretical origin is. It's too complicated to get into now, but it's important for many reasons. If you go to the next chart. And one of the aspects that we work in daily is making sure our space systems are robust to the space environment. And so this is what we call the spacecraft death chart, although the death part might be an exaggeration in many cases. But there are myriads of effects that can happen to space vehicles when we put them in the space environment. I won't go through all of these, but the ones that we're concerned about as far as the inner radiation belt are the single event effects in microelectronics and also the total radiation dose of the vehicle. Van Allen probes were designed to survive this harsh environment by making sure we had parts that had a high tolerance for total ionizing dose, and also we were able to make sure that our microelectronics didn't flip bits and do things in a drastic way when they went through the proton environment. And final chart is, again, why do we care? Our mission is covering the whole magnetosphere, all the particles that are important for spacecraft effects. And these histograms here show anecdotes from many missions through the past of the kinds of hazards that we see versus altitude, from single event effects at the top to internal vehicle charging and surface charging at the bottom. We're not talking about vehicle charging in this venue, but we can answer questions offline again. All these factors are important for every national security and every commercial system that goes into orbit, and the Van Allen probes mission is really going to rewrite the books as to how to define and specify the Earth's environment before we launch. Thank you. And now it's Nikki's turn to wrap it up.
Oh, I'm sorry.
No, that's okay. I was going to say, just to wrap up, just a reminder that we are not yet 100 days on orbit. As I think Dan said, our operational mission has only been a month, and I think, we've all been just amazed at the tremendous results that we've seen even at this early date. I would encourage you to come to the science session. We have a session on Thursday. The posters are actually tomorrow afternoon, and then there is a session starting after the break in the morning and going through the rest of the Thursday, where actually the 4 of the PIs will be giving invited presentations. Joe also has a science presentation this afternoon in the final session, I think 4 o'clock, yes. So please do come to those. You'll get a lot more information from those science sessions, and we can turn it over to questions.
Okay, we're going to take our first question from the internet. It's a question from Nancy Atkinson at Universe Today. And that question is, what has been the most surprising science finding thus far in this short mission?
Yeah, this is Dan Baker. I would say that we are looking now into the very throat of the accelerator, and I think we're seeing both spatial and temporal structure that we simply didn't know existed. We have nibbled at the edges before of the system from low-altitude spacecraft, from geostationary orbit satellites, but now when we're flying right through the heart of the accelerator, we're seeing much greater degree of variability, much greater structure that could only be hinted at from these more remote sensing. So it's sort of the difference between trying to look from a distance and looking right in the heart of the cauldron, that the accelerator cauldron that Craig was talking about. So I think that's, to me at least, from a particle standpoint, it has been that combination of the energy range and the time variability, the spatial structure, all the things that really have surprised us.
Yeah, I think I would only add that the other thing is there's been a lot of speculation about how things compete between things that cause the radiation belts to go away and those that cause them to get larger. And we're actually seeing that evidence now that those processes are competing with one another. It's still very early, so being scientists, we're cautious about making claims, but it appears that we can really start to understand this process that we've speculated about for a long time. And it's both gratifying but also very fascinating to see how that actually plays out, because we really didn't know before.
I guess I can just add one more aspect to what Dan and Craig have already said. So it's really early, and it's hard to put many years of work and beautiful results in 60 days into a few tweets. But the spatial distribution of the inner belt protons has really never been measured to this accuracy and across this wide energy range. So the science implications are going to follow, but it basically will enable us to determine what the particle sources and acceleration mechanisms are for those inner belt protons.
If I can just quickly,
that hasn't been done before.
I just want to add, I'd just like to say that whoever did the dance to make the sun as active as it's been in our first 100 days, I really appreciate that. And if any of you had a role in that, thank you very much.
We're waiting for the YouTube video of that dance.
I have one more question from the internet, and then we'll toss it to the room. This is from Marcia Dunn at the Associated Press. This is a question for Dr. Kitzing. What was your reaction when you first heard the chirping of the alien birds? And besides being an ultra-cool choral, what are the chorale? I can't say it
well,
right.
these waves.
What are the implications from a scientific point of view?
Well, these waves that we call chorus, because it sounds like a chorus of birds in the first morning. I've heard them before, particularly in my department, which has a long history of making waves measurements. But we make waves too, but that's a different topic entirely. It's the clarity, the fact that we can hear such a huge range of soft and loud things and how clean they are is really quite striking. We're just getting started on the parts of putting this together with the particle instruments to really understand how this acceleration process works. We were the first instrument actually turned on the spacecraft, so we've been watching them for a while and waiting eagerly for our partners that have the particle instruments, which tend to turn on later, to come up and start making measurements. And so we are now making coordinated measurements with one of the other key particle instruments that measures the electrons that we think that actually create these waves. But that data is still coming in. We have to coordinate the high time resolution measurements and get them in the right place. So it's a little bit of a waiting game at this point, but we're pretty confident we're going to see some really spectacular evidence of exactly how this process occurs, but we don't have it just yet.
Hi, I'm Irene Klotz with Reuters and Discovery Channel. I have a couple questions. The first on those chorus waves, had that been, I wasn't clear if that was like a new phenomenon or just, you were just saying that you're basically seeing it with clarity, and if it wasn't a new phenomenon previously, what was it known as, and what is the, maybe you can describe a little bit about what exactly that wave is, what it's being generated by.
So the phenomena has been known for quite a long time. Actually, even pre-spaceflight ham radio operators could sometimes hear it. However, the things that are new here are, one, that we have this full range of resolution so we can really understand the details. And the other, even from the scientific perspective, the most important is having a full three-dimensional measurement of that, of both the electric and the magnetic field of the cause of these waves. So these are essentially radio waves. They aren't sound waves. We can just play them that way. But we've had glimpses from a few other spacecraft with poorer resolution of the direction these waves go, but not like we're getting here. And this is the big new piece for us is if you look at the models, the theorists, you know, sort of, we need to know where they're going. And up to this point, all they could do is say, well, I don't know any better, so I'll say they're going this way with, you know, some little distribution around that. And so what we're starting to put together are the statistics of relative to what the sun is doing, where we are in the magnetosphere, going radially, sort of, or excuse me, you know, around sort of a clock from where the sun is located, to understand what the amplitudes of these waves are, what drives these waves. There are models of how people think these waves are created, but it's been a very, very hard problem. Even though the wave has been known for a very, very long time, the models have only in the last 5 to 6 years started to come about that can make something that sort of looks like Horus. It doesn't look exactly like it. So it's one of these very, very hard problems that comes up in physics that you work at and you work at and you work at, and now we're finally getting these measurements that we can put together and compare with those models and take that next step to really understanding this stuff well enough that they can go into a global model and maybe get to the point of actually predicting how things are going to behave.
Thanks. Also, the 1 billion electron volt that you were talking about, Dr. Mazur, had that been known before, that the energy level is that high?
Yes, it's been measured in low Earth orbit to that energy extent. But what we're able to do with the Van Allen probes is probe various regions where the particles are trapped. A lot of those particles don't, because of their motion, they actually don't have access to low Earth orbit. They stay at very high altitudes and they never come down. And so the energy extent, actually how far it goes, is it 1 billion, is it through 2 or 3 billion, that's really unknown at this high altitude, and so that's what we're going after.
I'm Alex Witzy with Science News. I have a general question for whoever would like to take it, maybe Dr. Fox. I just want a little bit more context in other spacecraft that have probed the radiation belts. There was a Japanese probe that I think Dr. Baker showed, and it was someone also mentioned trying to continue measurements so you didn't have a data gap. So what other probes have been looking at this sort of thing? And a corollary to that, why only now were the Van Allen probes launched?
There have been many missions that have that have studied the radiation belts. Obviously, they were the first discovery of the space age. So we've known they've been there for a while. There've been some very notable missions. The CREST spacecraft, which was an Air Force NASA partnership mission, which was in the early 90s, was the mission that kind of almost gave us all the questions that we're now able to answer with the Van Allen probes. So that was the one that really discovered how variable the outer radiation belt was, discovered many dynamic features about the radiation belts. We've had SAMPEX, which launched shortly, kind of overlapped it a little bit and then continued, very sadly re-entered just last month. So ended its operational life, and that was such a beautiful instrument, because a beautiful spacecraft, because it was on for so long. It was on for Joe, 20 years. 20 years. So we've had these continual measurements. So again, it's been sort of telling us what we want to go after. So they all really set the stage for designing and developing the science goals and the mission for the Van Allen probes. One thing I would add is we actually did turn on Dan's instrument, the REPT instrument. As Craig said, we usually leave particle instruments later in commissioning so that we've got all the deployments and everything done. We actually turned the REPT instrument on the very next day after Craig's instrument came on, so that we could do some final coordination between the SAMPEX mission and the radiation belt mission. So the Van Allen mission. Sorry, old habits die hard. So it was the instrument that most mimicked the instruments on SAMPEX. We could do some really nice studies, and we're looking forward to being able to get into that data. As to why only now, funding, opportunity. It's as I said, we've spent a long time knowing what we wanted to answer, what the questions were, and so this mission really is tailored to answer the questions that have been raised over the last 50 years.
Let me step in here. Oh, Dan's going to jump on this,
No,
but
go
I'll
ahead.
do. The ERG mission that Dan mentioned in the first graphic hasn't flown yet. That's
in development.
Right.
still in development. Nikki gave a summary of, I think, the top 2 or 3 science missions that radiation belt people would mention when they were asked about, what's been measured before. SAMPEX had a long lifetime, but it's only at low Earth orbit, didn't have the wave complement, wasn't able to characterize the high altitude interactions of particles and waves. And so that's, it's important, but it's not the whole picture. The CREST mission had a lot of overlap with the science goals that we have, but that mission only lasted 18 months. And so while it captured some dynamics, it didn't have the longevity that we need. It didn't have the energy coverage that we have by any means. The protons didn't go up beyond 100 MeV, for example, in my particular area of expertise. And so there have been glimpses, and there's probably a lot of feeling out there, just like I said, we've been flying spacecraft for 50 years, why don't we know this environment? And the fact is that, there hasn't been a mission just to target the science questions that we need until now, and this is the one.
And also with having the two spacecraft
Can I
is
answer too?
oh, I'm sorry, Dan.
Yeah, I'd just like to say that I think in the last decade or so that solar and space physics, or what we call heliophysics, has really focused a lot more on the duality of our discipline. There's the basic science of understanding the fundamental processes, but the NASA Living with a Star program really has tried to help us understand much better what are the impacts on society, what are the impacts on human technology. And so this program, the Van Allen probes program, is really a key part of looking at the connected Sun-Earth system. And it's really to understand the impacts on society and human technology. And so why now is because these programs are really reaching fruition. We're looking at the sun to understand the drivers, and now having these measurements from the radiation belt storm probes, the Van Allen probes, is going to help us complete the end-to-end picture. And I think it's very important to understand that maybe our discipline, more than most others in the sciences, really has this dual nature of both beautiful basic understanding of cosmic processes, but also understanding how that affects our daily lives.
I guess I just had one little piece to why now also is that really we didn't know for quite a while that they were as interesting as they are. You don't want to have your spacecraft sit in the radiation belts. So basically we avoided them. Many spacecraft go through there as quickly as possible. You see a little glimpse and it goes by. But until CREST and SAMPEX flew, we had no idea really that they were as variable and dynamic as they were. And by the time you start processing that and seeing what's going on and saying, we really got to go back here and figure out what's going on, that's just the time scale it takes to get a mission like this put together.
My friend Joe Allen at NOAA used to say that every object in space is an energetic particle detector, whether it wants to be or not. That includes astronauts. That includes almost every piece of hardware that's put in space. We're going there with a purpose, and I think we're going to meet that purpose very well.
Harvey Lightford, freelance. Following on that last comment by Dr. Baker, I actually wanted to ask Dr. Mazur, your last slide referred to the staggering number of satellites that are in orbit passing through the most intense areas of radiation. Well, even if we didn't know those belts were there, we would surely have noticed the effect on the satellites if it was that impressive. So I'm wondering, is this really a dangerous environment? And if it is, why wouldn't more satellites have just gone kaput?
Yeah, I think the focus, just to clarify what Craig said, when we talk about not spending a lot of time in the belts, it is the case that missions that you see there on the top, GPS, for example, is one that we rely on every day. GPS orbits essentially in the heart of the outer radiation belt in the electron-dominated region. And so indeed, systems are designed to work there 24/7, such as GPS. They handle the environment extremes through design. In GPS, they do use lots of shielding, for example. And so there are effects that occur, and the dynamics that we're talking about are scientifically interesting because we'd like to understand what the extremes might be. How hot can the outer radiation belt get? And that's not something that you measure on on a commercial system or something like that. It has to be done through science. When you talk about satellites that spend time sometime in the inner radiation belt, that's the region that people have really avoided. You stay in low Earth orbit, you're below the high intensity stuff which is way above you. Astronauts on the space station actually penetrate through high energy protons when they go through the orbit every day, but they're not really at the high altitudes where the effects might be a lot worse. And so while the whole, the staggering number of spacecraft actually, if they're in Earth orbit, they do go through Van Allen belts. And it's especially the outer zone that people have seen effects and have dealt with before, not the inner belt.
I'd just like to say that it's important, Harvey, both to design for the, real situation. To over-design is costly, to add more mass or to make the more elaborate designs. So if you're over-designing, that's a costly thing. Of course, if you under-design, you will suffer the consequences. And so finding the proper physical understanding and characterization of these regions is very important from an engineering and from a design standpoint, that you hit the sweet spot, and to do otherwise, either for the long term or the short term, would be very unfortunate and very costly.
We have another question from the chat. And this question is from Monica Young at Sky and Telescope. And that question is for Dr. Baker. In your talk, you mentioned that the belts were expected to be placid. Since we're approaching solar max, wouldn't we expect more dynamic belt activity?
It's a very good question, and we certainly do expect that when we have very powerful transient disturbances from the sun, what we call coronal mass ejections, we know the radiation belts respond to that. What we have seen, of course, is that this is a sort of a quieter than normal solar maximum. It's rising slowly to maximum. And we really have seen or we've seen hints, at least from past experience, that the most powerful drivers of the radiation belts are really the high-speed solar wind streams, and we were not expecting to see very many of those at this particular time. So I guess my remark is sort of a local thing, that just looking at the way the sun had been behaving lately and looking at the time of the solar cycle, that we hadn't necessarily expected to see so much activity concentrated in such a short interval of time. We've seen most of the kinds of interactions and processes that I'd hoped we'd see over 2 years. We've seen a lot of those in the first month or two, even before we were fully commissioned.
We're almost overwhelmed by how much we're getting. It's a huge amount of fascinating stuff to look at.
Jonathan Amos, BBC. One of the next great trends in spacecraft manufacture appears to be the all-electric satellite. Our future TV satellites, telecommunications satellites that operate in GEO will be basically have an iron engine put on them, and they'll take 4 or 5 months to climb to their operational altitude. What's the implications then for that great coming trend?
As far as engineering goes, you have to make sure that you can survive the long-term transit going up to high altitude. And so that's where, what Dan was saying, knowing having a very accurate specification of what you're flying through as you go up to altitude is really critical. Otherwise, you might over-design or under-design.
Yeah, it's very much an efficiency kind of thing, that if you know how long spacecraft are going to last, you know when to put the next one up rather than just park one and wait, and maybe you've had it sit there for a year doing nothing. But also, you want it to be right in that sweet spot, as Dan said, that as it goes up there, it's got just what it needs so that it's going to last. Was your remark about electrical propulsion, the nature of getting there?
They want to take the big apogee tanks out and make them much lighter so that they can go on a smaller, less costly rocket.
Well, I hope we will provide very good information for people who are trying to do that thing, to have much better specification and even possibly forecasting kind of capability to help people do that job better.
Good. And just one further question for Craig, if I can. You seem to imply that the chorus forms on one particular side of the Earth where, in relation to the sun? Could you just explain what's going on there?
Well, we know statistically it tends to be on that side. But again, this is part of having the global set of measurements we're going to get. As these orbits sweep around relative to the sun, we're going to actually be able to see the chorus all the way around. So we can really understand, you know, when we see an event from the sun that drives a magnetic storm, does it tend to happen here? Does it tend to happen there? The other thing that we're getting, which is really brand new, is that we don't know that if you see chorus in one local time, or one, you know, let's say between midnight and dawn, where we might have one spacecraft, what's happening right at dawn. And that's the comparison we're starting to see for the first time. And we are seeing that there are some temporal effects. That is, that it takes time for the chorus to maybe, it'll start in one location and then it will pick up a little bit further away. And that's something we're still just getting the first glimpse of now, to really understand, you know, and there's a whole variety of other ways we'd like to compare as well, which is why we want to have two spacecrafts. Because we've never been able before to say, oh, if I'm seeing it here, what's happening over there, you know, sort of a third of the way around or a quarter of the way around. And with the two orbits and the way the spacecraft phase, we can start to understand, we see chorus here, but maybe there's another kind of a wave, like an electromagnetic ion cyclotron wave, to throw a name out. And I see chorus first, and then I see that wave, and that explains this competition between things that create the radiation belts and things that destroy them, so we can understand why in one situation they get bigger, in one situation they get smaller. And that's one of the big puzzles, is we've seen signatures that would suggest we ought to get the same thing, and we get all three cases. They get bigger, they get smaller, they stay the same. And so we think it's this competition, but if you're only measuring in one place, you can never tell what's happening on a global scale.
I think this is one of the real trends in heliophysics, is to have multiple spacecraft in order to separate the space and time. But there's the famous corollary to Murphy's Law, which is Siegel's Law, that a person with one watch knows what time it is, a person with two watches isn't sure. And I think we're gratified so far. I see you got two watches. That's what made me think of it. And it's gratifying so far that the observations are of high quality and seem to give us a consistent picture. And I think that's going to be a very important component of what we do.
I'm sorry, but we're out of time for questions. So thank you very much, panelists, for your fascinating presentations and answers to our questions. And thanks, everyone, for coming to this press conference. Our next press conference is at 9 a.m. It's Fire in a Changing Climate and What We Can Do About It. Look forward to having you here then.